sense of timing.
A graduate student just going on to
I was Friday afternoon. Lining up a car, and we got a disability. That's one possibility. The other is the sharing the university district in Canada.
I think actually we need to everybody, I mean,
Just mention that, yeah.
and everybody.
Yeah. Yeah, between now and then,
So in my last lecture, I gave the main development for the distribution function of the b hat minus b. And today I feel that I don't want to spend very much more time on exact distribution theory, because I've got what I think of as more important approaches to finite sample theory that I need to have time for. So perhaps I can very briefly sketch the way that one can extend this to the k endogenous variable case without trying to go into too much mathematical detail. If you go back on the preceding proof, the reason for giving this proof in this perhaps rather extended form is that it can be very easily generalized in its initial stages by redefining b hat minus b as a vector, by taking the scalar which was ultimately called S and realizing that there's an equivalent positive definite matrix which occurs in the definition of the b hat minus b. The previous psi becomes a vector, and so on and so on. But then you find that what one is going to do is to write down, and the transformation from the b hat minus b to the q star goes exactly as before. The definition of the q star is as previously, obvious extensions, and one can then write down the joint distribution function of the q, the psi and the eta, with q star and psi both vectors of normally distributed variables, and the eta a Wishart matrix, a central Wishart matrix. So all those distributions can be written down as before, and then one has the same problem of first of all transforming from the q star to the f, which is a rescale b hat minus b. That goes through exactly as before. And then one comes to the big difference, which is that one is now going to integrate with respect to sets of stochastic variables which are the elements of Wishart matrices and the elements of normally distributed vectors. Well, these integrations are much more complex, but in a sense they are very similar to those that have previously arisen in the theory of multivariate statistics, particularly of Wishart and non-central Wishart matrices. And there are well-known techniques of doing these things nowadays, some of which depend upon multivariate Fourier transformations, and so are pretty complicated. But in fact, in this field, it is permissible to go ahead very much in the way that I did earlier, in simply expanding various exponentials of traces or products of a constant matrix and a Wishart matrix in power series, and then integrating term by term, so that you get similar formulae as before, which involve this kind of doubly infinite expansion in which each term is a power of some simple function of the Wishart matrix, for example, such as a trace of the Wishart matrix multiplied by another constant matrix. And when you come to making the integrations, you have a certain amount of symmetry, because it's the case that, as before, we've transformed the Wishart matrices so that they've got a variance matrix, which is the unit matrix. So you have this kind of symmetry with respect to the separate elements of the Wishart matrix, which ensures that you get a kind of similar symmetry in the polynomials that result when you do these kind of integrations. So you have a set of zonal polynomials which correspond to various terms in the integration. The typical kind of integral that one is always looking at, just to be a little bit more specific, is something like exponential minus a half trace some matrix, shall we say, G times a Wishart matrix S, and then something like a determinant S to some power, shall we simply say R, and then possibly some extra terms which are, if you like, just polynomial in S. So some function of S which is a simple polynomial in S with constant coefficients. And what one is doing then, which is slightly different from what we had before, is that we're integrating with respect to all the elements of S, given that S is positive definite, subject to the requirement that S is greater than or equal to 0, which simply is a way of saying that S is positive definite. So you have this kind of integration to work through, and as I say, you have to have appropriate formulae for such general types of integral. And you end up, as I said, with doubly infinite expansions, infinite series of such integrands. And so, as you can imagine, each element, each integral that you take is a complicated function of the various parameters occurring here in the GS and in the coefficients in the polynomials there. And the result is that except for very low order cases, or cases where convergence is very rapid, so you only have to consider a few terms, it's actually impossible to give numerical values to these integrals, because the various functions required have not been computed up to any very high order. Well, so I won't say any more about that, except that the theory is very difficult and somewhat elegant and not very useful. And instead, I will turn to something which hopefully is much more useful. That is the attempt to approximate these finite sample distributions, making use of general types of approximations and relying upon general theorems about the orders of magnitude of the errors in using these approximations. The advantage of these methods is that it's usually not very difficult to compute the approximation in cases where it's possible to use it, and very often that the approximation depends only upon a few functions of the parameters of the model, so that it's relatively easy to summarize the effect of the changes in the parameters of the model on the approximation. Well, so let me first of all make an elementary presentation of the area in which the main approximation I'm going to consider, which is the Edgeworth approximation, was developed. This was in fact in connection with straightforward central limit theorems, where what one is discussing is the sum of a set of identically, independently distributed variables. So that's the basic central limit theorem context, and what it does is to give you a better approximation than the central limit theorem, which of course is about the asymptotic normality as the number of members of the sum goes to infinity. Okay, so we define all this works by looking at characteristic functions we have some distribution for a variable x, a general distribution. We take the characteristic function, and of course we're going to assume later that it has various derivatives. We then take the log of the characteristic function, which is usually labeled the C, G, F for cumulant generating function. Well, now let's take the case that x, in fact, is a rescaled sum of identically independently distributed variables, and for simplicity, of course, you can easily look at the case where ut has a mean, but for simplicity, let's assume its mean is 0. Well, so but now, of course, what we have is a product of a set of independent stochastic variables as soon as we take the exponential as the product of the individual terms in the sum. And so this is just the same as that product. And of course we have independence, so that we can write this as the product of the expectations. Well, of course, each expectation is the characteristic function for the u worked out at t upon t to the half, capital T to the half, and so this is equal to the product. I'll use psi with a suffix u to mean the characteristic function of the ut itself, and then it's simply t upon t to the half. But you notice, of course, that this is the same in every case, and so this is just the tth power of that. And so we can write it psi u t divided by t to the half, all to the power t. Well, now, I'm sure most of you, of course, all of you have inspected this kind of thing before when you've looked at central limit theorems and their proofs. This is just the straightforward central limit theorem. And the basic idea of the central limit theorem is to, if you like, see what happens as t goes to infinity, what the limiting form of this characteristic function is as t goes to infinity. In order to get at that, let's now write it in terms of the cumulant generating function, and notice that it is again the same as t into now eta u, the cumulative generating function, t upon t to the half. And the obvious way that one looks at that limit is to take a Taylor series expansion about the origin, since for any finite value of t, as t goes to infinity, t upon t to the half, of course, is going to tend to 0. So you can take that Taylor series expansion of e to u as a function of t upon t to the half, and see what terms remain finite as t goes to infinity. Now, the point about the edge of the approximation is that rather than just looking at the limiting value of the function, one takes a higher order Taylor series expansion. To get the limiting distribution, all you have to do is to take the second order Taylor series expansion, or in fact, better still, the first order Taylor series expansion with remainder, and see what the limit of the remainder term is as t goes to infinity. But to get the edge of the expansion, what you do is to take a kth order Taylor series expansion and then look at the approximation you get as t goes to infinity. And of course what you will get is that the various terms in the Taylor series expansion, being powers of t to the t upon a half, will be of order, relative order, so that each term is t to the half less in order of magnitude than the previous one. So you get an expansion for the cumulative generating function in this kind of way. Now, before I go on to do all that, perhaps it would be useful for me very briefly to review some of the properties of the characteristic function and the cumulant generating function, which again I think you all remember when I remind you of them. What we would need to look at are the derivatives of the characteristic function and the corresponding derivatives of the cumulative generating function. So let's write the thing down. If we now proceed to differentiate with respect to t, we're going to make the obvious assumption that we can differentiate under the integral sign. That is perfectly valid, provided that the absolute value of the integral, that is the integral of the absolute value, is finite, and so let us see what the absolute value of the integral is. Well, we're going to make use of the idea that each time we differentiate with respect to t here, we're differentiating the e to the I to the x with respect to t, and all we get is an extra factor, which is just ix. So that if we do it r times, we just get ix to the r, and then we get e to the I tx dx. Alternatively, it's obvious by induction that if it's true for r, then it's true for r plus 1. Now, as I say, one criterion for this being a valid operation, taking account of the fact that you're integrating from infinity to minus infinity, you have to have a convergence condition, and the simplest one is the absolute convergence condition, which just requires that the absolute value of the derivative integral be finite. And in this case, you see that what you're going to get is that the absolute value is, if I just write the absolute value signs for the integral, is just, sorry, I should have said the integral of the absolute value, that's right, the integral of the absolute value is in fact equal to infinity minus infinity, fx x to the r dx, so that all that we require, of course the absolute value of I is 1, the absolute value of e to the I tx is 1, so that all that we require is that the absolute moment, the rth absolute moment, is finite. Now that is a sufficient condition for absolute convergence of the integral. Now if we now consider, and if that is satisfied, if the absolute moment is finite, then this is a valid formula. And now if we take it at t equals 0, what of course we get is that this term is 1, and so this is equal to I times mu, I to the r times mu r, the mu r standing for the rth moment. Of course, that's the rth moment about the origin, but in the circumstances that we're discussing, the origin is the mean. We fix that up. So this is also the absolute moment about the rth moment about the mean. Note it isn't, as I slipped into saying, the absolute moment, it's the usual rth order moment that we're discussing. Well, so now if we look at our Taylor series expansion, what we're going to get is that the derivatives of the likelihood function are the moments, and so we have a Taylor series expansion of the forms psi t. At this stage, I see that in my notes I've dropped the suffix u. Of course, what I'm going to state is general, but what the application is immediately in discussing this limit to the characteristic function of u. And we get the following. First of all, psi naught equals 1, general property of characteristic functions. Secondly, mu1 equals 0 because expectation ut equals 0. And so we only have the mu2 t t squared upon 2 minus I mu3 t cubed upon 6 plus mu4 t4 upon 24 plus, and then we have the remainder term. I'll simply write it psi 5 t star upon 120, and that means the fifth derivative of psi t worked out at some point t star less than or equal to t less than or equal to 0. Well, this is the one obvious expansion to look at, and I've written it down because clearly that's the terms that we're interested in some sense, but actually what we're more interested in is log psi t e to t equals log psi t, and what we really need is the Taylor series expansion for this. The corresponding terms in that Taylor series expansion about the origin are called the cumulants, and I will I could write down the Taylor series expansion simply with a kappa 2, a kappa 3, a kappa 4, and each of these would be a corresponding cumulant, and of course the point of starting with this is that you can immediately see by expanding this as 1 plus z, should we say, where z are the remaining terms here, and taking the expansion of log 1 plus z, then sorting out the powers of t, what the cumulants are. So one way of developing the cumulants is simply to expand the logarithm here in terms of 1 plus z, where z is the terms here. And so I'll write that down immediately, but note that theoretically this is just another Taylor series expansion for e to t. Now clearly the other thing I ought to say is that I'm assuming that the fifth absolute moment of the data of the UT are finite. Then each of these terms will exist, the fifth order derivative at t star will exist, and so on, so that That's a reasonable kind of covering assumption. Alternatively, one could assume that the fourth order moments exist and think about the form of the last term here, and its limit as capital T goes to infinity in the formula that I'm using above. But I'll do the easy thing, which is to assume the fifth order absolute moment exists. And so write down the formula in this way. The corresponding formula that will then turn out to be minus mu2 t squared upon 2 minus I mu3 t cubed upon 6. And then the T4 term comes partly from the first order term in the logarithmic expansion and partly from the second order term, giving you a t to the 4 from the t squared here, and that gives you plus t 424 u4 minus 3 u2 squared, the well-known cumulant formula. And then the remainder term is going to be yes, I see, in fact, I'm sorry that I've missed the t to the fifth out of this formula, t to the fifth. It's going to be the same as this, and unfortunately I'm a bit short of space to put it in, so let me just rub this out and replace it by the last term here. Plus t to the fifth eta star eta 5 t star upon 120. Now what we know about this e to the fifth t star term is that as in some neighborhood of t equals 0, this is bounded in absolute value by the fifth order absolute moment. In fact, that is true if you look at the formula involved for the absolute value of the derivative. You find that that is true for all values of t star. So that, let me simply point out that it's a simple consequence of the formula for the absolute moment that eta star t, eta 5 t star is less than, I'll call it mu bar 5, where the bar indicates absolute moment, fifth absolute moment. Well, now all we do is to take this formula and plug it in to our e to t. Now, I'll put back the u here and the u here, and then take these various moments to be the moments of the ut, and then, of course, I'm going to be using that I can rewrite this formula, which I have here, that psi t for the x is x in this way. I can rewrite that in the form that e to t is t times e to u t upon t to the half. Then plug in this formula for e to ut and see what we get. And of course what we get is since we've got t to the half, we have to substitute that for t throughout this formula, multiply up by t, and we find we get equals minus mu2 times t squared upon 2 minus I u3 t cubed 6 t to the half plus t for 24 capital T mu 4 minus 3 mu 2 squared plus, and then finally terms t to the fifth 120 t to the 3 upon 2, and then I'll simply retain, well, I might as well bring the t to the half in here.
First term divides 2, not t.
2, indeed. Well, of course, the first term gives you the usual central limit theorem. Because this is the characteristic function of normally distributed variable with variance with variance mu2, and we have the well-known inversion theorem, the limit of the inversion theorem, that shows that if the limit as t goes to infinity is a characteristic function, then the limit of the cumulative distribution function is the corresponding cumulative distribution function. So that gives us the central limit theorem. However, if we're now considering what happens in terms of a better approximation for large T, then we should have to have a kind of general theorem which showed that if we invert this, we take the inverse term by term and find that if we drop the last term here, we have obviously errors of order t to the minus 3 upon 2 in the characteristic function. Well, then one needs a theorem to show that one has the same order of magnitude errors in the cumulative distribution function. Well, in fact, there's no great problem in proving that. It's just a matter of separating out the integrand into the approximation and the remainder, and then showing that as you invert to get the CDF, that the integral of the error is of the same order of magnitude as the error in the integrand. That is not really at all difficult to do. So we have this general kind of theorem. The question is, of course, what kind of approximation do we get if we take this kind of a characteristic function and invert it? And that involves the following further approximation. This well, I've said verbally what I have written down here, so let me consider what happens when you take this approximation further. Clearly what one is going to do is to take psi t equals exp the first 4 terms here, but the important point is that we take the first term and treat it differently from the rest. And so let's write RT for all these terms except the first. Well, I better write all that up down then. Yes, I'm sorry, t cubed, t to the 4, plus, and let's retain the residual. Well, okay, I'll just write ot to the 5 upon t to the 3 upon 2. As I say, in fact, that is uniformly of that order, in the sense that if you take the t to the 5 outside, so if you multiply this by capital T to the 3 upon 2 divided by t to the 5, you have something which is uniformly bounded for t. And then what we can write is that psi t is exp minus mu 2 t squared upon 2 into st 1 plus st, where I'm simply defining st is equal to exponential rt minus 1. You see, it looks a little odd what I'm doing perhaps, but essentially all it is that I want to have 1 plus a remainder for my formula here, and clearly one starts off by having exponential RT here, because you're just taking the exponential of a sum, and so you've got the product of 2 exponentials, and then one is subtracting off 1, and the obvious reason for that is that as t goes to infinity, exponential RT tends to 1, and so this st is going to be of order t to the minus a half or less, capital T to the minus a half or less. And carrying through that corresponding expansion of st, one can again simply use a Taylor series expansion of st in powers of little t, and find that you have that it's equal to minus I mu 3 t cubed over 6t to the half, etc. Plus, and again, fourth cumulant plus something which is uniformly ordered t to the minus 3 upon 2 multiplied by t to the 5. And now we've got to integrate that with respect to e to the I xt to get the corresponding probability density. At this stage, let's drop the use of the mu 3 and call mu 3 kappa 3, my small kappa 3, mu 4 kappa 4, at least that simplifies the notation a little. Yes, I'm sorry, I've missed out an important term in the expansion. There's this further term plus a half mu 3 squared t to the 4 upon 36t, which comes from the expansion of the RT we have the second order term in the expansion of RT, giving you the square of the t cubed term here, and so though I've written it as t to the 4, in fact it's t to the 6, I'm sorry, t to the 6. Now the thing one now does is to integrate this term by term. In other words, one is going to make use of the formula, the inverse Fourier transform formula, that the probability density of x, let's just write that, f of x is equal to 1 upon 2 pi infinity minus infinity e to the minus I xt psi t dt. Notice that there isn't an I in here, which occurs if you integrate with respect to s, where s equals it. But if you do what I'm doing, which is simply to integrate with respect to t along the real axis, then you simply have the 1 upon 2 pi here. And of course you can separate out, just to interpret that again, you can of course separate out the causes and the e to the I xt into a cos and an I sine, and at the same time separate out the psi t into its real and imaginary parts, and you find that only the real part of the integral contributes to this only the real part of the product of these two factors contributes to this derivative. The imaginary part gives you a zero integral. But in any case, what we now propose to do is to substitute the first three terms here into this integral. The 1 here just gives you e to the minus mu 2 t squared upon 2. When you integrate that, you get just the usual asymptotic normal distribution. In other words, 1 upon 2 pi infinity minus infinity e to the minus itx e to the minus half mu 2 t squared dt is just equal to, well, I have perhaps the slightly awkward notation I, little I of x, given that I've got rather a number of alternative i's around. But that is just the usual 1 upon the square root of 2 pi e to the minus x squared upon 2, the usual normal density. Now the further terms you see that you get by now looking at the integral of the st times by e to the minus mu t squared upon 2 give you terms, well, I'll actually just write them all down. The further terms that arise from the st are as follows: 1 upon 2 pi integral infinity minus infinity, and you have minus I kappa 3 t cubed 6 square root of t plus kappa 4 t4 24 over t plus kappa 3 squared t to the 6 over 72. Yes, this of course is just a half times 1 upon 36 times t, all in a bracket, e to the minus mu 2 t squared upon 2 dt. And you see, in order to evaluate that, what you have to do is to know the following result, which is in fact exactly analogous to the relationship between the derivatives of the characteristic function and the moments of the distribution. But it's turned around in the sense that what we're now doing, so that t to the 6 should be t to the power 6, is to look at integrals which have got powers of t multiplied by a straightforward characteristic function. Now, consider then the formula that f of x is equal to 1 upon 2 pi exponential minus I xt times psi t dt, and consider differentiating this with respect to x. Well, of course, it's very similar to what we had before, assuming that the integral can be differentiated under the integral sign, that if we differentiate r times, perhaps I denote that as before by simply a suffix r, so this is the rth derivative of fx, we are going to get 1 upon 2 pi integral infinity minus infinity, and each time we differentiate this with respect to x, all we get is an extra factor minus it. So we're just going to get minus it to the r psi t dt. So that these integrands with the extra powers of t in them just correspond to the various derivatives of the the probability density function. So here, let's specialize this and introduce the notation IRX to mean the derivatives of the normal density, and the formula is just going to be the same. Yes, well, as we know, this is just e to the minus mu 2. Yes. T squared dt. Now, substitute that in here and write down the corresponding result, and we get the final integral approximation. I will not sort out everything in full detail, but if you check, you find that the kind of i's, minus i's to the r cancel appropriately, and so you just find that you have the following formula, that psi t is approximated by I of x plus, and then in fact the i's go out completely and you just have a simple formula over 24t minus, and the one thing that doesn't cancel entirely is a minus sign at this stage, I is 6x over 72t. Now, I noticed that way back I didn't quite give the right definition for my I of x. What I should have said is that I of x is that appropriate to a normal distribution with mean, with variance mu2 and mean 0, and that of course is in fact 1 upon the square root of 2 pi mu2 to the half exp minus x squared upon 2 mu2. In practice, what one very frequently finds is that in this field, people divide their x initially by the variance of the, by the standard deviation of the UTs, so as to get something with a standardized variance equal 1. And in that case, of course, you simply replace mu2 by 1. So let's assume that that has been done and that we've rescaled so that mu2 is equal to 1, which will simplify our subsequent discussion. Now, what I've done up to now is to look at the density, but equally we can look at the cumulative distribution function approximation. Yes, and here I said this is psi t, but it isn't, of course, it's an approximation to fx. And if we do that, we can find that the result of the inversion theorem is just to produce the integral of this approximation, and so you have a corresponding formula which is just obtained by integrating term by term, that fx is equal to, and now I'll use capital I x to mean the integral of the density, in other words, the cumulative density function for the normal distribution. And then, of course, when you integrate the derivative, you simply get the next lower derivative, kappa 3 I 2x on 6t to the half plus kappa 4, and then you get I 3x 24t, and of course finally kappa 3 squared I 5x upon 72t. Well, now the next thing, of course, and this formula I think is the one that is rather more generally useful, because after all what one's interested in is comparing confidence intervals and working out adjusted probabilities for example, asymptotic confidence intervals, and that involves working with the cumulative distribution function rather than the density. It's one of the conveniences of the edge of approximation that it's easy to integrate. So let's have a look now at what these various derivatives consist of. And of course it's easy enough to differentiate in our standard case where Ix is in fact 1 upon square root of 2 pi e to the minus x squared upon 2. It's easy enough to differentiate that and get the following kind of formulas. Differentiating the previous formulae again in an obvious kind of way. And so on.